Okay, in this lecture, we're going to be going over the introduction to single sample hypothesis testing, and this is just the sheet that goes over it. So for this, what you're going to be doing is just continuing on with chapter 9, and you can get to the online chapter 9 um, textbook by clicking right here. And it'll pick it up for you. And chapter 9 is, basically an overall introduction to hypothesis testing. But if you go down a little bit further, into 9.3 and 9.4, it really gets into the single sample hypothesis testing. And so just be aware, we already did cover quite a bit just in the introduction to hypothesis testing, and now we're getting into single sample hypothesis testing. Okay, so next, read through this overview sheet. You're going to be able to see a lot of information in here. Watch the YouTube videos. I'm making this one right now. And then this one's already made, this one's already made, so you should be able to access those pretty easily. Complete the homework problems on this sheet, and then submit it. And then complete the single sample hypothesis testing portion of the final project, and then submit a picture or file of the completed homework, and then complete the single sample hypothesis testing quiz. That's what you've got to do for this, and what we're going to do is go over the vocabulary really quick. I don't believe that we will cover this too much anywhere else, so this is actually kind of important that you're here right now. Maybe I should cover it someplace else, but there is something called an independent variable and a dependent variable. An independent variable is essentially the variable that is not impacted or changed by any other variable or factor. So if you've got two factors that are interacting, you've got one factor that is basically, hey, this is the factor that is impacting this other factor. This is, let's see. QBA students are going to be in one of four QBA 2302 classes. And we want to know how those students are doing coming out of those classes. And so we give everyone a test at the conclusion of QBA 2302. This is completely hypothetical. And we want to see, okay, how are these students doing compared or based on the classes that they're in? If they're really strong, being in this one professor's course, then we know that this professor is doing something that's, really strong in that area. Or if they're really weak in this other area, then so the professor would be the independent variable, and the student's test scores would be the dependent variable. So the student's test scores are dependent on what class those students are in. There's a lot of other situations like that, but a lot of times what you'll have the categorical variables that are are the independent variables, and then the dependent variables are normally dependent on whatever category they belong to. And that's basically what we're seeing right now is you have a lot of continuous variables that are independent, and you have a lot of continuous variables that are dependent on independent categorical variables. And so I'll do my best to really highlight those as we go through everything. So, what is the purpose of this particular test? What is the purpose of running a single sample hypothesis test? The main purpose is to compare a sample mean to a population mean. Notice we're comparing a mean to a mean. So you have a sample that has a mean, and you have a population that has a mean. And so we're just comparing a mean to another mean, and it's a sample, that is, part of the population. So it's a sample that's part of a population, and we are comparing that sample that's within that population to that population. One really great instance of this is with our election system. We have the Iowa caucus, those elections that occur up in the Midwestern area around Iowa, so on and so forth, and they go around. The Democrats and Republicans go from state to state, and um, they get their votes and run their initial elections, if you will, their primary elections in those first few states. And the reason why is because those states are very reflective of how well those individuals will do throughout the entire country. And so um, the sample from the Midwest area, between the Midwest and the East Coast, is used in the United States as a really great sample to determine how the entire population will vote. That's why they are the ones that are selected. Um, and so, you take that sample, and that sample is representative of the entire population to a certain extent. Next, we want to compare a sample to a population to determine if differences exist. For instance, if we have a sample of realtors. You look at all the realtors in Houston, just say that there's 2,000 realtors in Houston, and you want to compare realtors that are in their first 3 years of being a realtor compared to all the realtors. Notice what I said there. I'm not pulling the first three out compared to all the rest. I am comparing the first 3 years of realtors to everyone. So that includes themselves. So they are included in the population. And so if I have population data and I have the sample data, I'm comparing the sample to the entire population without pulling the sample out. Okay, so it's the sample compared to everyone, including themselves. Okay, and that's the big difference there between single sample and independent samples, which we'll get into later. So, and then also to determine if a population parameter may have changed. There's a lot more information about this in the textbook, but for instance, you have a sample that you know is representative of the population, and you want to know, okay, are individuals spending more money? Is the population spending more money at a particular realtor during this time? So you pull a small sample and you say, okay, based on this sample, these individuals are buying more clothes during the spring period of time. So therefore, we're going to run these sales. Or we run a sample to say, okay, based during the summer months, the tires wear down on our cars this much. So we took a sample of we initially tested them in winter, and now we're going to test them in summer. So we just take a sample of tires, and we look at those tires on how they compare on the population parameter of how fast they wear down in the summer compared to the winter may change. So next, assumptions. Here are the assumptions, basically what needs to be true in order for you to be able to run a single sample test. First, you need to have a one dependent variable that is measured at the continuous level. Like I was saying before, you've got a dependent variable that's measured at the continuous level. So with our examples of what we had earlier with the realtors, you might have um, the independent variable is the fact that they're a realtor, and the dependent variable is basically how long they've been, or sorry, the dependent variable is the number of years that they've been a realtor, really. So 3 years or less compared to everyone. And then the dependent variable is how much money they make. And how much money they make is a continuous variable. Also, the data is independent. So how much one realtor makes is independent of how much another realtor makes. And so I know for those of you who know about real estate, that's not necessarily always true, because you might be in a certain system that doesn't allow for that. So, that's something that you've got to consider. Is this really actually viable? And if it's not viable, if it's not really true, then you might want to consider a different test. And then also, there's no significant outliers in the independent variable. Um, and then the dependent variable should be approximately normally distributed. Um, should be approximately normally distributed. There we go. I don't know why that was there too. Okay, so let's take a look at so the amount that those realtors make should be normally distributed. So let's look at some hypotheses examples. Okay, so how should you write a null and alternative hypothesis? This is written out in such a way that you would be able to see, okay, this is how you'd write a non-directional hypothesis. This is how you would write a directional hypothesis. And I want to point something out to you. In the previous lectures, with the introduction, we have tails of tests. So this right here with the alternative hypothesis, the alternative hypothesis will always the symbol for the alternative hypothesis, this symbol right here, will always point in the direction of the tail of the test. Okay, so this right here is a where is it pointing? Is it pointing to the left or is it pointing to the right? Neither. It's not pointing to either side. This is a two-tailed test. So this is a non-directional hypothesis, a two-tailed test. Basically saying that the sample mean equals the population mean, or the sample mean does not equal the population mean. How would you write a non-directional test if the population mean, so the population mean, the known population mean is $59,456 $67, and I want to know, does this subpopulation, or does this sample, is it equal or is it not equal? Is it reflective or is it not reflective of the population mean? And so this is how you'd write the alternative hypothesis, saying, well, the null hypothesis says there is no difference between the population, there is no difference between the sample and the population. Okay, there's no difference between the sample that is being representative of a point estimate of a population. So the reason why it says mu here is because it is representing a point estimate of a population. So there's no difference between this and the population mean. Also, there is no difference between, and this is saying that it is not equal to the population mean. That the new mu, the new sample mean, or the new population mean is not equal to the old population mean. Okay, then how would you write a directional hypothesis if you expect the new sample mean is greater than the population mean of 59,000? So this right here is the null hypothesis. It's saying it is not equal to, or it is less than, that the new population mean is less than or equal to the old population mean. And this one right here is saying that the new population mean is greater than the old population mean. And notice that it is pointing in the upper tail. It is pointing towards the right, so this is an upper tail test. Okay, and notice that the sample mean, the actual value, I should put value, is never written in the hypothesis. Okay, in the null or the alternative hypotheses. So this is the effect size. There's a whole video that goes over effect size, but this is really important, not really covered in the book. So make sure that you watch the video on this, but this effect size is very important, and I suggest that you always calculate effect sizes to be able to say, hey, this is how noticeable it actually is. This is how much clout this has. Okay, so moving on, we've got a few questions. Let's see. Let's go through these questions. Assume that the null hypothesis, or the hypothesis says that there is no difference, says that mu equals 9, or the new population mean equals 9, and the alternative hypothesis says that the new population mean is less than 9. Okay? Um, assume the population standard deviation is known. Is this a left-tailed, right-tailed, or two-tailed test? Well, remember, all we've got to do is look at the direction of the alternative, and when we look at the direction of the alternative, we know that this is going to be, what is this going to be? If it's pointing to the left, then it is going to be a left, left, or lower tailed test. Okay, what is the test statistic? Well, notice right here it says assume the population standard deviation is known. So therefore, the test statistic is going to be z. Okay, because when we know the population standard deviation and it's a single sample test, it's going to be z. If we did not know the population standard deviation, then it would be t. With an alpha of 0.05, what is or are the test critical values? Well, in order to do this, you've got to know the tail. It's a left or lower tailed test. You need to know the test statistic, and now we need to pull up our fun little critical values sheet. Okay, so I'm going to come right here and go to Canvas, and I'm going to download the critical values sheet. So let's see here, Unit 4, and let's go to Printable Resources, Critical Values Diagram, and I just pulled up the critical values diagram, and you'll notice right here, here's the critical values diagram. And this is, you come down here, this is a lower tailed test, with an alpha of 0.05, and the critical value, yep, it's literally just written right there for you, is negative 1.645. Negative 1.645 for an alpha of 0.05. So what that means is that there's a 5% chance of committing type 1 error. So there's a 5% chance, assuming that the null hypothesis is true, there's a 5% chance of you getting a significant result just by chance, even though they are true, or even though they are the exact same. Okay. So, next, what is the probability of committing type 1 error? We already said that, which is 0.05. Okay. Next, assume the null hypothesis is that the new population mean, or that population mean, is less than or equal to 6, and that the alternative hypothesis is greater than 6. Assume the population standard deviation is known and that the sample size is 50. Okay. Is this a left-tailed test, right-tailed test, or two-tailed test? Well, once again, take a look at the alternative hypothesis. Based on the alternative hypothesis, it is a, what is it? Right-tailed test, or upper. Okay. Okay, so assume that it is not known. Okay, so what is the test statistic? Well, with what's that called? With, oops, hold on. With single sample, it's always only ever going to be z or t. So when we do not know the sample standard deviation, it is going to be t. Okay, so it is t is the test statistic, and then with an alpha of 0.01, what is the test critical value? So in order to determine this, we have to go to our fun t-chart. So we're going to go to our t-chart, which is right here. We're going to download the t-chart, and I've got my t-chart right here. And so what do we need to know? We've got a sample size of 50. We've got an alpha, let's see, with an alpha of 0.01 with an upper tail test. Okay, so with an alpha of 0.01 for a one-tailed test, okay, and then for 50, let's see here, coming right down here, 50. So we've got 50 right here, and then 0.01 for a one-tailed test is this row right here. So I think that Yep. So is it 2.403 because it's 50? Not exactly. It's going to be 2.405. Okay. 2.405 because we have to look at the degrees of freedom. The degrees of freedom is n minus 1. N minus 1. Okay. And then what's the probability of committing type 1 error? And that is going to be 0.01 or 1%. Okay, because the alpha is 0.01. Okay, then assume that the null hypothesis is that P. Well, I don't know why it says P. It should say mu. Assume that the null hypothesis says this, that mu is equal to 0.25, and that the alternative hypothesis says that mu does not equal 0.25. Assume the population standard deviation is known. Is this a left-tailed, right-tailed, or two-tailed test? You look at the alternative hypothesis, it is going to be a two-tailed test. Okay? Then what is the test statistic? The test statistic is going to be, if it's known, it's going to be a z. Okay. And then let's see here. With an alpha of 0.1, what are the test critical values? In order to get the test critical values, because it's a z-test and it is a two-tailed test, we're coming right up here with an alpha of 0.1. It is going to be, you can literally just copy and paste this, plus or minus 1.645. Okay. So there's a 5% chance of it being in the lower half, below the lower critical value. There's a 5% chance of it being above the positive critical value. But the critical value, in other words, the probability of you randomly getting a result that is above a z-value, or above a z-value of 1.645 or below a value of negative 1.645, the probability of that occurring is 10%. Okay. So, and then what's the probability of committing type 1 error? 0.1 or 10%. Okay. You know what I'm gonna do? I'm gonna come back to this in another lecture, and I'm gonna do 54 and all in one lecture together.